Sir, have already joined.
Yes, sir has already been joined. He is
Okay.
waiting.
Okay.
You can start the
Okay.
session.
Okay. Okay. So, good evening to all of you present here in our last technical session of 6 days FDP on quantum edge intelligence. This FDP is financially sponsored by All India Council of Technical Education. It gives me immense pleasure to extend a warm welcome to our distinguished speaker, Mr. Sudhindu Bikash Mandal from TCG Crest, Kolkata, who has joined us today as a part of this faculty development program. With rich experience and expertise in the industry, he brings invaluable insight that will surely help the participants to know more about quantum machine learning. We are truly fortunate to have Mr. Mondul with us today, and we are confident that his perspectives will inspire us to rethink, refine, and enrich our knowledge in quantum computing. A brief introduction of Mr. Mondul. Mr. Sudhindu Bikash Mondul is a highly qualified researcher with a master's in information technology from the University of Calcutta, specializing in quantum circuits and algorithms. His contributions are well documented through publications in prestigious journals such as Springer and IEEE Explore, underscoring his capability to produce high impact research outcomes. Crucially, Mr. Mondol possesses extensive hands on experience in Java. He treated as a Sun certified Java programmer and Python, essential programming languages for developing and implementing complex computational models. His distinctions as an IBM certified associate developer in QuickSkit quantum computation using QuickSkit V0.2x directly qualifies him to lead or significantly contribute to quantum computing aspects of the proposed work. His proven track record includes significant advancements in ternary quantum circuits and algorithms, which is a specialized area with potential for groundbreaking innovations relevant to this proposal's objectives. Beyond quantum computing, Mr. Mundell's diverse experience as a principal investigator in sensor networking for precision agriculture and as a research assistant in unmanaged ground vehicle development with prestigious DRDO demonstrates a versatile skill set in project management, interdisciplinary research, and, and practical system development. This broad expertise makes him an invaluable asset capable of contributing across various technical and strategic dimensions of the proposed project. On behalf of the organizing committee and all participants too, I extend a heartfelt welcome to you, sir, and look forward to an engaging and enlightening session on quantum Kolmogorove Arnold network and its application in quantum machine learning. Over to you, sir.
Hello, am I audible? Yeah,
Yes, sir, you are audible.
okay. First of all, thank you for inviting me. And there is a special thanks to Professor Dr. Mohuanundi and also organizer. Uh, First of all, may I share?
Yes, sir, you can share your presentation.
Sir, can you please confirm that you have joined your two different devices?
Yeah,
Okay,
because
sir. Can you tell
from
me the
one
second ID so that I can make it the co-host? Otherwise, it will
second,
be difficult for you to manage.
uh, both the same ID
Both
actually.
same ID, right? Okay, sir.
Yeah, both the
Let me
same ID.
give me 1 minute. I will keep that. Hopefully, you have now the co-host access, sir.
I don't know.
Yeah, sir, I can check it. You are co-host from the both of the devices, so you can
I
take it from here.
I think I'm able to share.
Yeah, sir, your screen is visible and your audio is coming clearly.
So today's my topic is quantum circuit synthesis of an approximate hybrid Kolmogorove Arnold network. Okay, before going to this topic, I know for this today's session in I think today's first session, Ritojit actually explains what is quantum computing and there is some what are the different noises and how to mitigate this noise. I think he delivered very nicely. Uh, but before going to the main topic, I want to give you the very basic idea about what is quantum computing and what is the state of the art of recent quantum machine learning. Then I can deep dive on this topic. Hope I think I will not be a more technical in this talk. Uh, and I have one request. If you have any question, you can ask in between my talk. I will never mind. And also, they, I think I will not make you bored. Next time. Okay. So, first of all, for today's my topic's goal and objective is that how what is Kolmogorove Arnold network first of all. Then, is there any classical machine learning solution exist or not? And then, uh, uh, how can we implement this Kolmogorove Arnold network in quantum computing devices and especially in Nix era devices? Uh, and I think all of you heard then what is the meaning of NICS, and actually NICS means a noisy intermediate scale quantum computer because still our qubits, I think from the Rityojit's talks, all of you are familiar with what is qubit, at least terminology. I'm not expecting you all of you know what is the actual deep dive of qubits and what is the different technology. But I think all of you heard the terminology at least. So now qubit is it's not a PO, and there is some noise due to the lack of challenges in design of this hardware. So every hard problem nowadays implement in this present state of the quantum computer is really challenging. Uh, so we try to implement this Kolmogorov Arnold network in NESCA. And what is the difference between this Kolmogorov Arnold network from the present classical machine learning or quantum machine learning? So let's start. Before starting, nowadays everyone says there is a quantum computer, quantum computer. So all of you know the quantum computer and why it is different from the other classical computer. Uh, all of you know the classical computer knows the bit. Here it is a unit of information can be stored in a qubit. And what is qubit? A qubit is quite different from the classical bit. Basically, classical bit is we can say it's a complete deterministic bit, and it has a two state, and you can observe it analogically. If light is on, then you can say state one, light is off, then you can say state is zero. All different kind of some voltage is there and ground state is zero, something. And we use these deterministic condition to encode our information. But in case of quantum computer, by using the we can say law of the physics or quantum mechanics or postulates from the quantum mechanics, we can say qubit is different from the classical bit. For the definition purpose, we can say qubit is a superposition state and superposition of logical 0 and logical 1, or some more technically you can say superposition of two basis steps. But analytically, what is this? What is this observation? Actually, qubit is not a deterministic bit. It's a probabilistic condition because quantum mechanics belongs to a mathematically, it's in a probabilistic domain, not in a deterministic domain. So before going to this quantum computing talk, try to switch your thought process and switch your brain from the deterministic world to probabilistic representation. Analogically, we can say what is a qubit and why it is powerful. Suppose we have a two ball, one is red ball, another one is green ball. If I put one of this ball without showing you into some basket and or some box, and if I asked which color contains this, which color ball contains this box, what will be your answer? You can't say deterministically this one is red ball or this one is maybe a green ball or green ball. You can't say deterministically. Like in classical beat, if there is some some information collecting situation like your LED bulb or something voltage measurement, you can definitely say that it is 0 state or 1 state. But if the ball within the covered box, and if I ask this question, you are unable to say that determines whether a ball is red or green. Rather than you can say by guess, yes, this ball is either there is a fair chance, 50% chances to their red ball or 50% chance to green ball. This is the actually a qubit analytically. And power of this superposition we can use to store information and which will give you the extra degree of freedom for computation. And today's talk, I will not discuss the details of the power, what is the power of superposition, how can we get advantage for designing algorithm, because this is not the scope of this topic, but try to understand that superposition give you the extra information. Another analogically, you can understand why it gives you the more information. As per the Shannon's entropy theory, or I think all of you know from the classical Shannon entropy theory, if the probability of outcome is less, then it contains a measure more information than the other system. Similar like that, for the ball under the cover in a box, you have there is an uncertainty condition and you have no total knowledge base about that. There is no difference. That's why it contains more information about that. So this is the superposition state of this qubit, and we will use the superposition power to design our quantum algorithm. Next is quantum measurement. It's a very interesting thing. Quantum measurement actually, see, as a human being, we are in a deterministic world. So we can measure or we can understand anything in deterministic way. So, but qubit in superposition state, that means it's a probabilistic state. So we have required a measurement operator. What is that meaning? Suppose there is a box and within this there is a ball. Now I open this box. Now you can check what is the color of this box. Either it will be the red color or it will be the green color. Opening this box means actually a quantum measurement. That means you can come from the probabilistic world to the deterministic world. By measurement, you can measure the what is the present state. And within the box as a closed box, you have do some computation there with the power of this superposition, because qubit in a superposition state, you have done all of this computation within the closed box. But if you want to get the result, then you have to open this box, and after doing some operation, there is a changes within this ball or everything is changes. Now you open this box and get your result. That means quantum measurement, it transition from the probabilistic world to the deterministic world. Then another very important properties of quantum computing is entanglement. Entanglement is kind of correlation. It is coming from the quantum mechanics idea. I'm not going to details explanation of quantum mechanics where it is entanglement is come, but rather to give you the analogical idea. In superposition state, there is a superposition of two basis states, and there is a probabilistic bit of information. That's why it's called qubit. But entanglement is actually correlation between these two qubit, and it makes a different kind of correlation. And by doing some operation between these two, suppose we have a two boxes, and within these two boxes we have a two different qubit, and from the outside we have do some operation, some types of operation. I'm not giving the good type of operations we have to do. Take it as a black box operation. You have done some operation, then there is make a one correlation between these two different boxes. That means two different qubit. And what type of correlation? That means after doing some correlation, if you just separate these two boxes, then if you open the another one box, then you can automatically get the idea of this other box. Again, I want to give you the one analogical example of this quantum entanglement. What is actually this? Suppose we have two gloves. One is left-handed gloves and another one is right-hand gloves. We put these two gloves into different boxes. Now we have to do some correlation and something and separate one box and one box from and you some person can keep one boxes and he or she can move from this one position to the another position, say from the one universe to another universe. After doing that, he opened the box, and if he finds the within this box there is a left-handed glove, then automatically he or she can understand other box contain the right-handed gloves. This is the makes a correlation. This type of correlation actually build up after this quantum entanglement, and we have done this quantum entanglement with the two different operations. This one is the one properties of quantum computing, and we use these properties to make a good quantum algorithms. And then there is an interference because in quantum mechanics there is a two type of interferences, destructive as well as constructive interference. We have also used this interference to make our quantum algorithm, which will be different from the classical algorithm. So now I want to give you the very brief idea about what is the pipeline structure of quantum computer. All of you know the basic structure of your classical computer. In the previous talk also we have understand so many different processor architecture and other things. Similar case of in quantum computing, there is a quantum processor, and there is a different type of quantum processor exist in terms of making principles. Some quantum processor makes with a superconducting material, some is ion trap material, and some is photonic space quantum processor exist in real life still now. Then what is the basic pipeline architecture? See, first you have to define your problem statement. And what is the problem statement? Problem statement may be, suppose there is an unstructured data, you want to find some value or some element from this unstructured data. That could be your problem statement. And from this problem statement, you have to define or you have to write your quantum algorithm by using the properties of quantum mechanics like superposition, entanglement, or other things. By interference, by using these properties, we have to design your algorithm for finding in our example for finding an element from an unstructured data database. And so all of you know, if you heard the quantum computing, then you will be the familiar of this algorithm name. This is called a Grover's algorithm. And this is developed by Love Grover. He is Indian, and it's a very famous algorithm whole world. And so you design algorithm by with the help of this quantum properties. Now you have to translate this algorithm to a programming languages There exists so many programming language nowadays in quantum computer. One programming language is Cascade. This is developed by IBM. Another is SARC. This is developed by Google. And there is also another programming language. This is called Penguin, and this is developed by Xanadu, photonics-based hardware programming languages. And also there is also another programming language called Python. This is developed by Regedi. And so your choice, you can write your program by using any of these programming languages. So, but there is a constant. You have to choose programming language according to your quantum hardware. Otherwise, you have to use a different cross compiler exist nowadays. Or you can familiar with one programming language, then you can write, and according to your hardware, you can use the cross compiler to compile it to your own processor. So there is another terms you will find. This is called a transpiler. What is that transpiler? Actually, transpiler translate your programming language to your architectural level code. What is that meaning? In quantum computers, still there exists a different kind of topological architecture machines. Like ion trap machine is a one-to-one connectivity machine, but IBM use a heavy hexagonal connectivity machine, and others computer also use different kind of connected architecture machine. So transpiler's first job is in programming language, you define every your algorithm in terms of logical operation. What are these logical operation? Logical operation is like this bit flip operation, Hadamard operations, or I think from the Ritoji talk, all of you are familiar with this gate, this logical and there is a synod gate and Toffoli gate. They are the logical representation of your algorithm. But your quantum hardware may not understand of this all the logical operations. They have a own set of particular physical instruction. So first transpiler convert your logical logical gate level representation to the your physical instruction set. Actually, for example, Hadamard gate is logical gate, but from the physical quantum computer ends, there is no Hadamard gate. Hadamard gate can be decomposed in some micro instruction. This is depending on the different quantum computer to different quantum computer. In IBM use different decomposition rules. IonQ, this is ion trapeze. They also use different logic to decompose, but they have own basis gate set. So transpiler convert your logical gates to the physical gate set. Not only this, they also do some optimization work, like your quantum circuit. They try to find some identity so that it can optimized in circuit optimization. Means your circuit there is a two dimension. One is horizontal dimension and one is vertical dimension. Vertical dimension actually says that how many number of qubit requirement, and horizontal depth actually gives you the how many number of micro instruction or instruction is required to implement your algorithm. So optimizer in transpiler there is an optimizer. Optimizer try to reduce the depth, that means horizontal part depth of the circuit, so that your circuit or your instruction can be executed in within a limited time. Because in this one is very challenging nowadays for quantum computer, because our quantum computer is noisy, so it has a qubit decoherence time is very less, so it start decohering very fast. Again, I want to say what do you mean by decoherence? Suppose qubit state is 1, but unlike classical computer, if we want to stay our state 1, it will remain unlimited time of unlimited, not by technically, but it can stay in state 1. But in quantum computer, if I after making one quantum state as a 1, it will not remain in the same position. Due to the noise, it started decohering. And with the noise, it started shifted from the one state to the other state. So, it will generate some error in your computation. So, circuit depth reduction is very essential, or circuit optimization is very essential still now, so that we can do our all the operation within the difference time of the qubit, so that we can get a very good result. So circuit optimization is a very essential part of the transpiler. Then after doing this transpilation, it will generate a chasm level or assembly level programming, where it holds some micro instruction architecture wise micro instruction. Then you will find the analog instruction. What does that mean? That means after generating the micro instruction or physical gate instruction, you have to convert this instruction to a pulse level pulse generator. What is that? If I can say, typically in case of superconducting qubit or superconducting quantum computer, superconducting qubit can be stored in a dilution refrigerator. There, because temperature qubits are very temperature sensitive uh, in case of actually superconducting. If you have a superconducting, it's a very temperature sensitive. So we need to put into the dilution refrigerator. But our electronics device, that is non-cryogenic electronics device, is outside. This electronics device actually generates the pulse so that it can modify your qubit according to your instruction. This analog instruction is generated from the non-cryogenic electronics devices, and after going some probes and cable, it entered into your dilution refrigerator and modify your qubit. In this way, actually, total quantum computer works. Now coming to the direct point, what is quantum machine learning? I think all of you know the classical machine learning, and in case of quantum machine learning, what we actually do. Before going to this, there is a very famous picture left corner. If you heard,
Incoming voice call from
বলো
hello,
বলো কেন নাম হ্যাঁ মানে
hello, any
Uh,
question?
no, no, no. Please, organizers, kindly mute yourself. Speaker is interrupted.
Okay, no issue. Actually,
Sir, very sorry. Very
no,
sorry.
not an issue. It's fine. It's fine. So in the left corner, you will find this picture. This picture is very famous nowadays. If you any kind of quantum machine learning talk given by any researcher or any professor or any industry professionals, they will refer this picture. Actually, machine learning problem we divided into four different types of not in terms of model type, but in terms of data, we divide it into four different types. One is classical data and classical machine learning. I think all of you know this classical data and classical machine learning. Then another part is classical data, but machine is or quantum machine learning model is quantum computer. Another part is your data is quantum. What is quantum data? Suppose you have a sensor, quantum sensor. It will you have a quantum gravimeter, then it will generate a quantum data, not a classical data, like only the voltage or something like that. But quantum the sensor can generate the information, like you have a interference information, there is with the voltage information, and others information also find with this. So this is the quantum information, and this is generated from the different quantum sensors or some quantum mechanical operations like a Hamiltonian simulation or Hamiltonian operations, it will generate the quantum data. So there is a quantum data, and you want to use this quantum data for classical machine learning model. That will be the another type of problem statement. And last problem statement is quantum data and quantum machine learning. And in this AI era, classical machine learning problem statement is, there is a lot of work already has done. But classical data quantum machine learning, still there is a huge number of works already done. But I can say there is some drawbacks of these works, and there is a so many loopholes also there, and researcher is struggling due to the noisy state quantum machines. And so there is so many problems, and there is a good research area still exists in classical data and quantum machine learning problem. And there is a quantum data and classical machine learning. There are very few works, not a few works. There is so many works exist, and all of these works are from the physicist era. They use quantum data for finding the phase by using the different quantum machine learning, classical machine learning, like Boltzmann machine, or they use some reinforcement learning to check the phase, what will be the phase if I have a quantum data. But because phase information is very much needed information in terms of the physicists as well as from the chemist, they also try to understand the after the molecule to molecule interaction, there is a data. By using classical machine learning model, they try to find or predict what will be the molecular interaction. So there is also some work already exists. But in the domain of quantum data and quantum machine learning, there is a very few works already done in this area. But today, my concern, I will discuss only the classical data and quantum machine learning. And our setup, this Kolmogorove Arnold network, is also a classical data and quantum machine learning problem. And before going to this other slide, I want to say that there is a so many quantum algorithm exist. One is quantum phase estimation algorithm. This is actually fault tolerant algorithm. And quantum, by using this quantum, because calculating the phase or estimate the phase of a quantum state is very difficult. So we can do different tricks by using these feedback properties of the quantum computer. You can encode the phase in a different qubit, and from this qubit you can get an information. This is the main fundamental area of quantum phase estimation. There is a quantum amplitude estimation. This one is also another fault tolerant algorithm. Quantum Fourier transform, then HHL Grover's algorithm. These all are the algorithm are fault tolerant era algorithm, which is very difficult to implement in nowadays Nix era algorithm. So there is a Nix era algorithm. This is called variational quantum circuit algorithm or variation quantum algorithm. This one is quantum and classical hybrid algorithm. Suppose we have an algorithm. There is this algorithm. Some part is very much required computational complexity demands, or it demands more computational power. This part we can do in a quantum machines, and less resource demanding part we can execute in a classical computer. This is the main motivation or of this hybrid quantum classical algorithm. One of this FDP quantum variation of quantum algorithm. This is in this case, quantum circuit actually holds a parameterized circuit, and we start with some guess parameter, and we do some quantum operation, and after this measurement we try to update this parameter by using the different optimizer, which will execute in a classical machine. This is the main principle of, and they also use the variational principle of quantum mechanics. And there is another algorithm, QAOA. This is quantum approximation optimization algorithm. This is also a powerful quantum classical hybrid algorithm. Different kind of optimization algorithm you can implement by or optimization problem you can implement by using this QA algorithm. And QA algorithm also you can use for your machine learning problem statement. There is also another quantum circuit board machine and quantum Boltzmann machine also exist. Now come into the quantum machine learning part. In quantum machine learning, actually, we are concentrating classical data, and machine learning model is quantum computer. So in this case, first challenge comes, how can we encode the classical data into a quantum computer? Because in our machine learning problem, you have a data set. This data set is a classical data set. You have a features, and according to these features, you have some outcomes corresponding to the data point. Actually, there is a vector. So how can you encode this classical data to a quantum computer? This one is the first challenge in quantum machine learning. So there is a three straightforward scheme exist. This is not a limited. There is a scope for researcher. You can develop a new scheme to encode the classical data to a quantum computer. There is a lot of scope for a researcher. But there is still now exist three different schemes, and they have a advantage as well as disadvantage also. First of all, basis encoding technique. In this case, suppose you have a data, that means you have one vector. How can you encode this? You have to, this classical data, you have to convert to a binary data. Each and every data point, like 0.1, you have to convert it to a binary data, and 0.8 is another data, you have to convert it. And also after converting this data in binary data set, then you have to require and suppose you have required 5-bit or something 6-bit, that's your choice for converting this classical data to a binary set. Then also you have required another extra bit like for showing it for getting the sign bit. If data is your classical data positive or negative, you can use another extra bit for showing the sign. So after converting this bit, each and every bit can be represented as a qubit in quantum computer. In this way, you can encode your classical data to a quantum computer data. But in this case, you have required a huge number of qubit. Say for encoding a one data, you may require a 6 qubit. Now, suppose in classical machine learning problem, you have a features. There is a 1,000 features. And within 1,000 features, each and every data representing, you have required a 6 qubit. So for the 1,000 features, you have required 6,000 qubits. This is the main disadvantage. There is no quantum computer exist which will give you this amount of qubit. Now there is a best publicly available quantum computer will provide 157 qubit. So this is the main design, but very easy to implement, and it demands less number of quantum gates, because only you have a qubit. If your qubit in all are in 0 state initially, just you have required a Pauli X operation to convert from 0 to 1 according to your binary data. Only Pauli X operation is required to encode this data. So in terms of number of operation, it's very advantageous and very easy to create. But in terms of demand of qubit, this basis encoding is not realistic still now. So next is amplitude encoding. This one is very efficient, very efficient in terms of qubit, because in quantum computer, single qubit can store at a time 0 plus 1. That means it's a superposition, 0 and 1. So at a time it can store a 0 and 1. So in the 2 qubit, how many data you can store? It's a 0001 1011, all possible combination of 0 and 1. So at a time you can store a full number of data. In 3-qubit, similar way you can store a all possible combination of 301s, that means 000 that means 8 data. So for n-qubit system, you can store a 2 to the power n number of data. So, in 3-qubit, you can store a 8 data. For 4-qubit, you can store a 16 data. So n-qubit, you can store 2 to the power n data. That means you have a n number of features. Then your qubit demand will be a n number of qubit required. Suppose you have a 1024 number of features in your data set, then it's demanding a qubit number 10. Just within a 10 qubit, you can store your 1024 number of features. This is the power of amplitude encoding. But there is a very disadvantage in terms of to implement this, we have required huge number of quantum operation to just only encode this quantum classical data to quantum data in the amplitude of the superposition state of qubit, because it's required so many multiplexer kind of operations as a micro instruction. So it requires huge number of 2-qubit operation. That means 2-qubit number of gate, like C0 gate, you have required huge number of. For an example, for you have 1,000 features, 1024 number of features data in classical data. You have to encode by using an amplitude encoding to a quantum computer. You have required a 10 qubit. It's a very advantageous, but you may require more than 20,000 number of 2-qubit gate. This is very impossible to run in your local nowadays mixed quantum hardware, because as we know, in earlier slides I told you that there is a qubit is now fragile, so it's more error prone, so it start decohering. So transpiler job is to reduce the quantum circuit depth. But if there is a 20,000 number of 2-qubit gate, and 2-qubit gate is more error prone, so it will introduce more and more error in next era computing. So in next era setting, this is also a very difficult approach to amplitude. If your data set is very small, like 32 data features or something, then it is maybe implementable by using amplitude encoding. There is another encoding technique. This is also named as angle encoding technique. This is very easier to implement, and it's also demanding a less number of qubit than the basis encoding, but higher number of qubit demand from the amplitude encoding. Here we actually use qubit to store the classical data. Like for example, here for 0.1 this classical data we can encode in the phase of the qubit rotation, because you know qubit can exist in your Hilbert space. For analogically, how can you visualize? If you have a globe, within this globe surface, if you draw any point, this is as called a qubit. So by using this qubit rotation, you can store any number of classical data by using the different kind of rotation, like Rx rotation, rotation about the x-axis, rotation about the y-axis. You can also store these. But here, qubits requires, if you have a n number of features, then you have required n number of qubit. So it is required a less number of qubit than the basis encoding, but it required high number of qubit from the amplitude, but it is very easier to implement, and it's called a Niskera encoding system. So for if you have a 100 features data set, then you have required 100 qubit here. And 100 qubit is nowadays is available, and also your circuit for encoding classical data, your circuit depth will be within the reasonable cost. Okay. So now I want to describe the traditional, what is the traditional structure of the quantum machine learning. So there is a three part of this quantum machine learning. Now still all Niskera, all the quantum machine learning problem is actually variational, depending on the variational principle or variational quantum circuit. So first you have to encode the classical data to a quantum computer by using the any of the encoding technique like basis encoding or amplitude encoding or your angle encoding. That is your choice according to your features and with the advantage and disadvantage of this encoding. First, you have to encode your data. Then you have to require one PQC circuit. PQC is a parameterized quantum circuit. This is sometimes terminology, it's called answers. So these answers called a one starting wave function, you can say. Actually, in machine learning problem, everything is a function. So by using this parameterized circuit, parameterized quantum circuit, actually just wait one wave function is actually representing. So you can start with some wave function. This is for the case answers and with some parameter. And after doing the measurement, you can calculate the estimate value. So again, I'm starting from the, you have a data set. So there may be a 1000 or 2000 data points exist. First, you encode one data point to a quantum machine. Then you have a starting PQ circuit, parameterized quantum circuit. And this is called variational quantum circuit. And first, your input is your data point encoded in a quantum machine. Then you apply this parameterized quantum circuit with some case parameter. Then you estimate this value. And for the supervised learning, this estimate value, you try to check it is very closest to your data point or not. In this way, all the data point you execute like a similar like your classical machine learning. And here you calculate where you calculate the some outcomes. Here you calculate the expected value or expectation value. According to that, you then goes to the different optimizer. Estimated, you have an actual value and you have an expectation value is called the estimated value. From there, it will make a one cost function. Then you goes to the classical optimizer. Classical optimizer then update your parameter. And again, it's starting from executing your data points and comes. This is the loop. According to this loop, you will find the ultimately you have to find out which parameter actually says your correlation between this your input data point and what will be the best card uh, for your data point. This is the basic structure of the quantum machine learning, and sometimes this is called quantum neural network structure is also similar like there is a quantum support vector machine. There is a different kind of setting. I'm not telling in this lecture. And this from the researcher point of view, you have to design this PQC circuit in such a way so that it can be the least number of quantum operations, but it can also find your correlation between your data features. So this is actually done by some parameterized gate as well as some entangling gate. You can find this entangle gate is this control rotation gate or your entanglement operation. And you know what is entanglement analogically at least. So from this, and also in quantum computing, every circuit is unitary circuit. And you can't actually in normal machine learning, what you have a function, cost function, then you make the derivatives of this cost function and goes one by one. Similar case of there is a this PQC circuit actually your cost function, and you need to derivatives over, but unitary there is no, you can't able to do the derivation of the unitary matrix. So there is a one rules. This is called parameter shift rules. Now from this picture, you will find where is parameter shift rules. Actually, suppose there is a n number of parameter in your quantum circuit. First, you can hold one, choose one parameter and others parameter will be the remain same. And for this parameter, you shifted it for pi/2 rotation and then calculate the estimate value. In this way, you can find the gradient of your PQC circuit or quantum circuits. This is the actual structure, very basic structure. In details from the researcher's point of view, we have to design a very good cost function. And for this PQC circuit, design is the challenge according to your problem statement. And also, there is a issue if you have a if you give the more entanglement in your PQC circuit, there is a thumb rule. If you give the more entanglement between your qubit, then your circuit's expressibility is higher. That means it can learn almost a different kind of most of the functions of your choice. But if you introduce more entanglement, then there is a chance of parent plateau issues will come. So there is a lot of work still we researchers need to do. How can we avoid parent plateaus to finding the best PQC circuit for our problem state? So this one is a challenge from the researcher point of view if you want to do in quantum machine learning. Now come to our today's talk. This is the Kolmogorove Arnold network based quantum machine learning. First of all, what is Kolmogorove Arnold theory? That is a very interesting thing. Suppose you have a multivariate function. You can learn or you can approximate this multivariate function as a superposition, or rather say linear superposition of a univariate function. This is a Kolmogorove Arnold theorem. This is classically this algorithm is very strong algorithm. If you want to read the proof of this algorithm, you can actually go to the mother paper or best paper of this Kolmogorove Arnold. They prove that there is a very strong proof also exists. If you have a multivariate function, you can learn this multivariate function or approximate this multivariate function as a superposition of a univariate function. Each and every function, if you learn and make this superposition, and there is an outer function, then you able to approximate the multivariate function. This is the main principle of Kolmogorove Arnold network. So, our Kolmogorove Arnold theory, sorry. And what is the Kolmogorove Arnold network? It is actually slightly different from the from your neural network point of view. In neural network, if from the black box end or from the high end, what we can say, there is an input feature state. Then you make some correlation and define intermediate features, and these intermediate features, after that you make and how can you make this? There is a weight coming from the each and every edges from the node, and these weighted average or weighted sum in the intermediate intermediate state or in intermediate layer. Then you apply some activation function, then it goes, and there is ultimately there will be the output, and then you, according to your demand, you can use either softmax or use sigmoid according to different activation function you can use. So this is the normal structure of your neural network. But Kolmogorove Arnold network is slightly different from this point of view, from this working principle point of view. In neural networks, activation function is fixed, and there is a learner is your weight and bias. There is a learning parameter, and each and every layer you have a predefined activation function. But in Kolmogorove Arnold network, each contains the functions. This each and every univariate function. This is actually a learnable function. So your activation function is coming from the edge and then sum up into the intermediate layer. There is no fixed activation function. Here, activation function is learning. That means each and every univariate function. From the Kolmogorove Arnold theory, we can learn multivariate function as a superposition of univariate function. So univariate function coming from the each of the input features, and then they superposed in a intermediate layer. So activation function here is a learning parameter, not a fixed point. There is a difference between the Kolmogorove Arnold network and neural network. In nowadays, there is so many works has been done in classical computing by using Kolmogorove Arnold network. There is a very nice paper. So many. That's why it's a new kind of things actually inspire us to make a quantum version of this Kolmogorove Arnold network. Actually, two motivation behind this. One is can we represent different kind of networks in quantum computer, as well as there is a superposition of univariate function. So can we use the superposition principle to make this linear superposition of the univariate function to represent the Kolmogorove Arnold theorem to a quantum computer, and will it give some advantage? That was our motivation to make this Kolmogorove Arnold network. So very quickly, there is a very less number of paper by using quantum Kolmogorove Arnold network base. First paper is proposed by Bikash. This one, they have proposed this quantum Kolmogorove Arnold network setups, but their setup is in fault tolerant era. Their setups can't be executed in a Nix era quantum computer. So this gives another motivation for us. Is it possible to make a Nix era settings for this Kolmogorove Arnold network? So we are going to first we studied this paper and analyze this paper. What is the problem and how we can solve this problem? Actually, this is the Kolmogorove Arnold network settings. As I have already told you, there is an input feature state, and there is a every phi is your univariate function. This is coming from the edge, and they have different kind of linear superposition, linearly superposed in each and every intermediate state like this. There is a superposition of univariate function exist in each and every node. So function is learnable function here. And from the evoscope settings, there is a huge number of ancilla qubit required, as well as they have required huge number of 2-qubit gates. So their settings is not implementable in Niskera. So what is our settings? I think I will be finished very easily. So in our settings, there will be so many mathematics, but I try to skip because otherwise you will feel bored. I think I may also making you bored. So and there is two mathematical, so I will skip it very first. So in our settings, you know from the Kolmogorove theorem, there is a superposition of univariate function. Then what will be the univariate function? In our setting, we choose univariate function as a Chebyshev polynomial. Why Chebyshev polynomial? I'm not explaining. If you want to know this, then you can read our paper. In Chebyshev polynomial is a very good, its behavior and its root is also good properties. I'm not explaining that. Don't want to be more technical. So there is they have a good properties which help us to make a quantum circuit very easily. That's why we choose a Chebyshev polynomial as an inner function. And this one is and also we can say there is a weighted Chebyshev polynomial. This weight will be the learner weight for the Chebyshev polynomial, and Chebyshev polynomial is a very good properties. And one univariate function, we actually use a sum of degree Chebyshev polynomial, any degree of Chebyshev polynomial. Suppose if you have take a order 5, then there will be sum of order 1 polynomial, order 2 polynomial, order 3 polynomial, order 4, and order 5. If you go for the higher order, then function will be the more smoother function, and it has the ability to learn any complex function. That's why order is very important. And also here also our tricks is there. How can you, if you choose very higher order but circuit depth will not increase, this is actually our main USP in our settings. I will explain it then later. So d degree Chebyshev polynomial can very good way approximate the any univariate function. This is I'm not going to explain because that will be the more technical, more mathematical. But if you want to know this, there is a Chebyshev polynomial. Is look like it's actually expansion of cos and theta, and there is some few terms of this Chebyshev polynomial. Is T0 is 1, then T1x is degree 1 polynomial x, and degree 2 is 2x square something, and some this 2x square minus 1, and degree 3 4x square, and something like that. And if in degree its eigenvalue is actually oscillates between the -1 to +1, this is also help us to design our quantum circuit. In our case, in our setting, we use in every univariate function as a sum of your choice degree number of polynomials. If you choose a 4th degree polynomial, then this is the sum of degree polynomial. So here you can see if your degree is 4, then highest degree of polynomial will be x to the power 4. Then after doing the all terms polynomial for degree 1, degree 2, degree 3, degree 4, up to that, you will get all the polynomial terms in the sum terms. And also, there is a radical expression of your Chebyshev polynomial is look like that. So if you scale down your x is your data point or your features, if you want to know in classical, if you have a feature set, then x will be your features. And if there will be n number of features, then in your Kolmogorove Arnold setting, there will be n number of univariate function. And each and every univariate function we actually express as a sum of degree order polynomial. This is our setting. So you can x is your features. So you can scale down your features from 0 to 1. Then if you are able to features this, then you can rewrite your mathematics in this way, and we'll find each and every term can be written as half of e to the power IR theta plus half of e to minus IR theta. So this one is the expression for one terms. Now, in case of innate order, I can see in degree order, see that I can move. If you sum all degree 4, then you will find the one polynomial. What is this polynomial? This is your polynomial. But it is really required all the terms to sum get this polynomial. No. See, if we add these two Chebyshev terms like T3 and T4, then you will find all the terms like x to the power 4, x square, x cube, and x and 1. All the terms you will find. In sum, there is, I have done the 4-term sum. There is also exist all these x to the power 4, x square, x cube, x square, and x terms. And also see that in last degree 2 terms also giving the same terms. Coefficient may vary, but by using the sum of the last two, if your choice of degree n, then in nth degree terms and nth minus 1 degree terms, if you add, then you will find all the terms. By using this theory, we can, and also we have done this proof. I'm not saying this proof. If you interested, then you can also find out paper. Within paper, we have mentioned this proof. So by using the highest 2 degree of this polynomial, we can approximately only the coefficient terms will be changed, but all the degree, all the polynomial terms you will find within this. If you add this highest 2 degree terms, we can approximate the sum of the all terms of Chebyshev polynomial. That means that is our univariate function term. So we need to just make the quantum circuit of this expression for a one features. These are so by using this mathematics, if we able to make the quantum circuit for this mathematical expression, then we easily encode the one univariate function. Similar way, all the univariate function, if we able to make the quantum circuit or able to transform this mathematics to a quantum circuit, then we able to express all the univariate terms. Then by using the superposition principle, we can make a superposition. This is the our designing philosophy of this quantum Arnold network. So, and for making this, we have required this different two qubit gate. I'm not explaining this. So, so from this, there is another thing. Just from this showing this mathematics, can you design a quantum circuit? No. So you have to do step-by-step process from this quantum mathematical expression to quantum circuit. How can you do? In the slides, I try to present one thing. Suppose you have a two-feature system as an example, and then you have required a one qubit because we use amplitude encoding based technique. But reasonably in our settings, we are able to reduce the circuit depth. This is the another advantage of our Kolmogorove circuit. We use amplitude encoding, but still we have required less number of 2 qubit gate. So here in this way we can use mathematical step. This is very boring to explain all these things, so I'm not explaining. You can use this 2 qubit gate if you are familiar with Stoffoli gate, or if you are familiar with CNOT gate, then very easily you can understand this structure. This is actually basically a control operational gate, and see that this e to the power I d theta, that means e to the power I d theta and e to the power I theta to n. Here theta 1 represent the features 1, theta 2 represent your features 2. We have designed this control operational gate, and see that we have e to the power di theta. This is the nth degree of the Chebyshev polynomial actually encoded in this control operation gate. And here just to represent that we have required dth degree terms, we have required two terms, d theta and I minus I d theta. So that's why we have required two control gate. One is e to the power I theta 1 d and theta 2 for two features. If you have a n number of features, then there will be the n number of diagonal terms will be exist in your quantum circuit. And see, if you have a matrix step is 8 cross 8 matrix, then you have required 3 qubit to represent this unitary matrix. Similar, like here, we have a n number of features, then theta 1, theta 2, theta 3 up to theta n will be exist as a diagonal terms to represent these first terms of this mathematical expression. So if it will be the n cross n matrix, then to represent this n cross n unitary matrix to a quantum circuit, we have required n number of qubit. And similar way, we also represent minus I d theta. Then for d minus 1 theta, we have required this matrix, and d minus 1 theta, we have required this matrix. So we have required four matrix with different dimension, and matrix dimension will be depending on the number of features. But these four matrix actually represent the four terms of this mathematical expression. So if you have an n number of features in your machine learning problem, then your matrix dimension will be n cross n, and every diagonal elements of this matrix holds your features, corresponding features, each and every terms of this mathematical expression. Now, our next task, by which quantum operation we can add all this matrix. That's why I'm skipping this mathematical expression. Just a minute. So by using this LCU-based circuit means linear combination of unitaries. By using this linear combination of unitaries, you can able to add the matrix. Suppose any case, forget about this Kolmogorove Arnold network. If you have a problem statement, if you have a unitary matrix and you want to make the add of this unitary matrix, or you want to make a linear superposition of this unitary matrix, then you have to use a LCU circuit. This is called linear combination of unitaries, and this is done by some oracular circuit. This is called a oracular circuits, or LCU circuit can be implemented by using the oracular. What is that meaning? If your state is 0, 0, then there is, suppose you have a 2 qubit, then by using 2 qubit, how many number of state you can generate in quantum? 0, 0, 0, 1, 1, 0, and 1, 1 number of state. So by using and what is control operation gate? From the Ritojit talks, I think all of you know what is control gate. If both the qubit, if both the control bit is 1, then target bit will accelerate, or target bit operation will be activated. Like this in your series circuit, if there is a 2 switch, if you on this 2 switch, then your light will be on. Similar like this, a control gate actually works in this way. If you have a 2 qubit, if this 2 qubit is 1, then so 0, 0 state, how can we convert it? By using this Pauli X operation, we can convert it to the 1, 1. Then after this 1, 1, this unitary block, unitary matrix. What is this first block unitary? Your e to the power I d theta part is coming. And in the seconds within this 0, 1, because I have shown you, we have required 4 terms. Yes, we have required 4 terms from the mathematics. E to the power I d theta, e to the power minus I d theta, e to the power d minus I theta, and minus I d. So these 4 terms, actually we have required 4 matrix. Fine. And matrix dimension depending on your input features. If you have n number of features, then log of n number of qubit will require, and matrix dimension will be n cross n. And how many number of matrix is required? 4. So come into our circuit architecture. We have a 4 matrices required. These are our 4 matrices. And how can we add this? By using this LCU circuit. So if within the 0, 0 statements, your first matrix, 0, 1 means your second matrix, 1, 0 means your third matrix, and 1, 1 means your fourth matrix. And you see, this matrix dimension is depending on the input features. There is a input features. If you have a, and I'm saying log n number of qubit, if there is n number of features, your matrix depth is n cross n, and this n is can be represented as a logarithmic complexity or logarithmic number of space complexity. You can represent it. And there is a 4 matrix, and these 4 matrix can be added, because if 0, 0, and we are making there is a Pauli operation. If state is 0, 0, then forcefully we make it 1, 1, and other state will be the different. So only 1, 1 is this 2 qubit now. So this matrix will be activated. Then 0, 1 terms is coming, then this matrix will be activated, and this matrix, and all this matrix will be added and make it as a linear superposition within this 2 qubit. So in this way, we actually represent the Kolmogorove Arnold theorem, where each and every univariate function can be represented as a linear superposition. And as a nutshell, we have or as a summary, we have a matrix n cross n, 4 types of matrix according to our mathematics, because we use univariate function as a weighted sum of Chebyshev polynomials. And to represent this sum of order degree in Chebyshev polynomial, we have required 4 terms. So for each and every feature, there is a 4 terms. And we have n number of features, that means n diagonal matrix. So there is a n number of function according to your features. So your Kolmogorove theorem, there is a n number of univariate function. So n number of univariate function represented within the one by one matrix as a Chebyshev polynomial, and Chebyshev to represent the sum of them, we have required 4 terms. That's why we have a 4 matrix. Each and every matrix diagonal element contains the each and every univariate function, and after summing this, we will find in this ancilla qubit, there is an ancilla qubit, we'll find the sum of all the univariate function, and each and every variate function also a sum of Chebyshev polynomial of degree order or d degree. So we, by using this circuit, we are able to achieve this, make the Kolmogorove Arnold theorem. And also we have required n number of log n number of circuit to represent, and log n 2n plus 1 number of circuit required to assume the outer function. So by using this circuit, we actually represent the Kolmogorove Arnold theorem inner function. But in Kolmogorove theorem, there is an outer function also. These outer function actually represent by the measurement operation. So in this way, we can represent our quantum circuits in a Nix era setting. And we have also 2 qubit number of gate demand is very less. If you have a 8 number of features, then we have required only 120 number of 2 qubit gate, but still it's exponential. We are working on this. We try to make it a linear number of 2 qubit gate. And this is our total circuit, total pipeline of our QCon. Here we represent the Kolmogorove Arnold theorem, and after getting this measurement operation, we will get the outer function, and by using this some weighted mixing of this outer function, we get a final outcome. Suppose if you have a in-class classification problem, then there will be n number of nodes. Then you make softmax. This is very popular, like your classical machine learning problem. Then you loss calculation and go to the classical optimization optimizer. Then this is a feedback loop. In this way, our CON will execute. This one is the first we have proposed the Nix era. Ivaskov first proposed the fault tolerant era version of this Kolmogorove, but from the Nix era version, we first proposed this structure, and our present published paper, we try to show that we able to make the quantum circuit, but we gives a very simple workout from the if you are very familiar with classical and machine learning researcher, then you can say this is the very simple problem. Classical machine learning can very easily, yes, I'm accepting classical machine learning can execute very well for this our data set, but we use this toy model to establish our network quantum architecture is fine or it's correct kind of things. That's why we use this toy model. We established our model, but in our future goal is to execute very large number of data set. So here in quantum machine learning, we'll get this kind of accuracy. Just I'm showing this result. And also we apply this synthetic dataset, Swiss roll dataset. Actually, we try to check that our model can learn the non-linear data set or not. And see that in our Nixera setting, there is a only single layer of Khan architecture. There is no multi-layer architecture is there. So within this single layer, it can learn with a 75% accuracy. Still, we are working on that non-linear data set, how our Khan behavior. And we also use this spiral data set. This is also a synthetic data set for this our paper. We have also tried this, and we have get not a good result. And we are not claiming that we can outperform the any classical machine learning problems. Till now, we are not claiming this. Actually, in our paper, we try to claim that this QCon architecture in next era, our proposed architecture can work, and it can also learn the simple data set as well as from the non-linear data set point of view within the single layer of this Kern structure. It can also just learn with some good accuracy from the classic. Again, I'm not saying that we are claiming that we outperform the classical network. It's only the establishing the model structure in quantum machine learning era. And mind it, in quantum machine learning, still our quantum machine is noisy, so it can gives a very bad result. And reasonably, if your circuit is very high, then it will reduce your performance also. So these are the right. And in future plan, actually, we are executing for the high like MNIST dataset and Cipher 10 dataset in a quantum hardware, IBM hardware to testing our model is scalable with a high feature set, and what will be the result will coming. This one is we are working on that, and also we try to test our this QCon in a NVIDIA GPU system in QQuantum. We also got a project in this as a domain, uh, and we are working on Alzheimer's dataset. And also in quantum machine learning, distributed quantum machine learning designing is very, very difficult task because there is a highly entangled circuit exists for the quantum neural networks. But our circuit, there is a less number of, there is no point of entanglement. There is a, we use superposition principle actually in our designing technique. So make it a distributed environment is easier. So we have already designed but not published. In upcoming paper, we'll publish the distributed QCon. And also there is a less number of, or there is no entanglement issues in learning parameter. So we are able to avoid the parameter to shifting, which is a very common issue for quantum neural network. And also we try to make our QCon as a federated setup, as we say that our circuit design in such a way so that it is very easily distributedly we can execute for a different, because it's a superposition. So we can cut circuit cutting is less costly, and reconstruction also a very easier task. So we can use our architecture also federated learning setup. And list. This one is our collaborator, Dr. Shian Choudhury is in same in my office, and Turbushu is actually he was intern of our team. Now presently he is in not doing his doctoral degree in North Carolina University, and Arnav is also working as a pre-researcher with us, and Professor Amlan Chakraborty, as well as there is Professor Sebrekais, he is from North Carolina University. He is renowned chemist professor, and he also visiting professor of MIT and Berkeley. This is our team, and this final side. Thank you.
Thank you very much, sir, for such a lucid explanations of so-called some complex architectures you have covered. Thank you very much. Participants, if you have any queries, you can raise either unmuting yourself so that you can directly communicate to our respected speaker, or if you wish, you may post your queries through the chat box. Our speaker, Mr. Mandal, is ready to answer all of the queries that you are supposed to raise. If you have any queries right now, then you can, without hesitation, you can raise. So hopefully they do not have any queries because it is
I heard
continuous fourth
session.
sessions
I
actually.
know, I know.
Y-
And also
Yes.
Saturday, and there is a week.
Not only Saturday, sir, but also with actually it is a last day, last session,
I
and
know.
our session it is the third session of today.
Yes,
So
I
they were
know because in
continuously attending the sessions.
and also Ritojit also told very basic things and everything is right. So
Uh,
listening this
so
too much
yes.
talk is very difficult. I know it.
So anyway, sir, yeah, if the participants, if you wish to make a contact to our speaker, Mr. Mandal, in future, you can also able to contact if Mr. Mandal allows you to
Yeah,
communicate.
yeah,
Yes,
definitely. You can send a mail anytime. You can also communicate via mail will be better. So you
yes,
can
yes. So
anytime.
definitely we will upload the presentations of today's deliberation. And in future, if you have any queries, you can directly interact Mr. Sudhindu Bikash Mandal in future. So thank you very much, sir, uh, for your presence and so-called a very nice deliberations of the so-called complex topic. So we wish in future again we will be connecting for our future FDPs alike. Thank you very much, sir. Thank you.
Thank you. Thank you.
Thank you, sir. Thank you.
All the participants are requested to please fill up the feedback forms of the last day and also requested to go to the ATAL portal and give the test. Test will be for 1 hour and of 25 questions. And if you face any difficulty regarding ATAL portal, please inform us immediately in the chat box and meet us at 7:30 p.m. in the valedictory session.
So all of you us will meet on valedictory session sharp at 7:30 p.m. Thank you.